Fatigue is a condition at which an object undergoes repeated motion and the object after some time will experience weakness or tiredness. Okay, and this is also occur in our muscles when we do constant running. After sometimes we will feel muscle tired, okay, or also known as fatigue. Okay, this phenomenon is also occurs in metals. Okay, metals will experience weak or fracture due to repeating load or repeating stress that we apply to the metals. And this contributes to 90% of mechanical engineering failures. The examples of fatigue in metals, including the continuous load and unloading applications, for example, bolts and shafts. Okay, they are used in many materials or many applications. After we do the continuous loading and unloading, it will experience fatigue. Okay, so the fatigue is also we can say it's a premature failure, okay, or lowering of the strength of a material. Okay, as we do the repetitive stress, the stress may be below or above its yield strength. Okay, after we do the repeating stress, it will undergoes or it will experience fatigue. Fatigue occurs if these three criteria are met. When stress is applied to the metals, it can be tensile stress or compression stress, and this stress or this load is applied repetitively, or we apply this stress continuously, it will later will form plastic strain or permanent strain, yeah, or also known as permanent deformation, and later on it will undergo failure. Okay, if these three tensile stress and these tensile stress are applied continuously with cyclic loading, and then it will later on experience plastic strain. So if these three criteria are met, then the material may fail. Okay. Mechanism or process of fatigue occurs in three stages. The process occurs by the fatigue crack initiation, which is this step, where a small crack forms at some point of high stress concentration. Now, normally this occurs at the surface, okay, due to the formation of small crack, okay, where we put the high stress concentration on it, followed with fatigue crack propagation, in which during this step the crack increase with each cycle stress, okay, with each stress cycle. And finally, the final failure, which occurs very rapidly once the crack reached a critical size. We call it as catastrophic rupture. And this, when we look at on the image of a fatigue failure, we can see there are two surfaces, okay, smooth and crystalline surface. Smooth surface here is due to the process of initiation and propagation, and crystalline surface or rough surface is due to the fast fracture or catastrophic rupture. The region of a fatigue surface that formed during the crack propagation step can be characterized by two types of marking. Okay, on the crack propagation step, okay, there are two types of marking. One, we call it as clamshell or beach markings, and another one is striation. Okay, so this area here is the crack propagation step, and when we enlarge this, we can see the second types of marking, which is striation. Okay, while fatigue striation, this one is a microscopic view where we can only see this kind of striation step or markings by using electron microscope, either SEM or TEM. While beach markings or clamshell markings, we can observe this with the naked eyes. Okay, we don't have to use any microscope. Okay, and each striation, okay, this stripe here, okay, represents the distance of a crack, okay, during the load cycle. Okay, if we again enlarge this one of these striation, we can see, okay, we can see the distance between the crack, okay, that we load with the stress continuously or in cycle load. Okay, this striation consists of intrusion and extrusion. Okay, so if you can see from this image, the intrusion at which the stripe is going into the metal, and extrusions is due to the crack that occurs out from the metal. Okay, so that's why from the image of beach markings here, we can see one part is a smooth surface and another part is the rough surface, which is due to the presence of intrusion and exclusions from the striation. In general, there are three different fluctuating stress versus time graphs that we can see from this slide. Okay, the first one is reverse stress cycle, in which the stress, if you see this graph, it's a x-axis is the time and y-axis is the stress value. Okay, and this is our zero value. Okay, for the reverse stress cycle, the stress alternates from a maximum tensile stress, which is the positive value here. Okay, positive value here, and it alternates with the minimum compressive stress value, okay, which indicates the negative value here. Okay, so if you can see maximum tensile stress, okay, up value, positive value is tensile stress. It will alternate with the compressive stress negative value, and this will occur several times throughout the time. Okay, and then the second type of fluctuating stress versus time graph is repeated stress cycle, okay, in which the maximum and the minimum stress are asymmetrical relative to the zero stress level. This is our zero stress level, and this maximum and minimum are not symmetry with the zero stress level here. Okay, so from this we can identify the value of sigma m, which is mean or average stress, sigma r, which is the range of stress, okay, maximum value and minimum value, and sigma alpha here, which is the stress amplitude, okay, the height of the stress. And the third type is random stress cycle, or also known as irregular stress cycle. Next part, we will be talking about SN curves, which is graphs that show stress as a function of number of cycles. Okay, so this is done experimentally in the lab to identify the amount of stress a material can handle with several thousands number of cycles, or to identify the number of cycles under certain amount of stress. This slide shows the SN curves for two different materials, which are tool steel and aluminum alloy. You can see from this graph, SN curve is made up from the number of cycles as the x-axis and applied stress as the y-axis. Okay, the materials that we have here have the similar SN curve trend. Okay, at the beginning we have similar SN curve trend. Okay, where as the number of cycle is increased, as we increase the number of cycle, the stress of material will decrease. Okay. However, for tool steel, after some cycle, the curve becomes horizontal. Okay. After some cycle, which is at large cycles or large N value, okay, the curve becomes straight line or becomes horizontal. And we call this as endurance limit or fatigue limit. Okay, while for alloy, aluminum alloy, it does not show a fatigue limit. Okay. With this SN curve, we can identify the fatigue life. For example, if you look at this point here, when we apply about 90,000 psi of stress, the steel will experience up to roughly 10,000 or 100,000 cycles before it becomes fatigue. When the materials are being used, and if it's experienced a fatigue, there are several factors that will affect the fatigue life. We will be discussing some of them. Okay. The first one is the level of stress or the magnitude of the stress applied and the quality of the surface. Okay, this SN curve here, okay, stress versus number of cycle curves here, shows the effect of different level of stress applied to the materials. And as we can see, as the stress level is high, the fatigue life is lower than the much less level of stress. Okay. In terms of quality of surface, we can improve the quality of our surface material, okay, by doing some introducing some procedure. Okay, for example, in this case, we give or we applied short pinning. Okay, where small shot is applied on the surface of the material, and the effect of this, it improves the fatigue life of the material. Okay, so these two factors of fatigue, magnitude or level of stress and quality of the surface, we can do several things. For example, to improve the fatigue life, okay, we can apply polish the surface, or we can introduce compressive stress into the surface layer. Okay, for example, shot pinning or high-tech technology, high-tech method, which are, for example, ion implantation or laser pinning. Okay, this to improve the surface of the material. If we improve the surface of the material, and then we can improve the fatigue life. Okay, and there are other several ways to improve fatigue life. Okay, either by doing make the outer layer of the materials harder, or avoid internal corners or notches, etc. Fatigue life also influenced by the environment at which the metals or the materials is being used. And there are two environment effect on the metals, either thermal fatigue or corrosion fatigue. Thermal fatigue, for example, brake disc. Okay, the brake disc in our car or motorcycle, we use the brake and it will grip the disc, and if we do this several times, after some times the brake will get fatigue, will experience fatigue. Okay, so what is thermal fatigue? It's thermal cycling causes expansion and contraction. Okay, we know applying heat will make the metal experience expansion and contraction. and then thermal stress will occur. Okay, this graph shows as how the SN curves of different temperature, how how the fatigue life depends on the temperature, and the solution for avoiding thermal fatigue to occur is either by change the design, or we can use materials with low thermal expansion coefficient. So if it's a low thermal expansion coefficient, that means we can increase the fatigue life of the material. Another environmental effect that can give impact to our fatigue life of materials is corrosion fatigue. Okay? Where the chemical reactions will induce pit, which as the stress rises. Okay, this is normally occurs if we use the materials at in the seawater. Okay, so there are various type of chemical reaction can occur in the seawater. Okay, as we compare with the same material exposed to the dry air. Okay, if you can see from this SN curve, the SN curve for material that exposed in seawater has a lower fatigue life as compared to the same material exposed in the air. Okay, so corrosion can be avoided by decrease the corrosiveness of the medium. So we can do any electrochemical process on the surface, or we can add protective surface coating and add residual compressive stress.